So I think our audience is going to find the next topic really interesting. And Tony, thank you for making the time to do this. I find it encouraging to hear that in some circles, small modular nuclear reactors are being seriously considered as one of the many solutions to the big energy transition. And then thinking about how project production management can play a role in helping make that feasible. So our speaker today is Tony Rollstone. Tony established and teaches on the Nuclear Energy Master's Program at the Department of Engineering at the University of Cambridge. His research interests are in the economics and safety of nuclear power with a focus on SMRs. He is leading several SMR research projects in the UK. Also, he's involved with projects on the industrialization and the economics of fusion and the design of energy systems for net zero in 2050. Impressive background, impressive work experience. Tony, look forward to hearing what you have to say. So I'll turn it over to you if you'd share your screen with us, and I'll let you take it away.
Okay. Right, so something slightly different, something with a takt time of about 10 years, nuclear reactors. And this is more scene setting about the potential for lean methods to work in nuclear to address its inherent weaknesses. And Gary mentioned people serious about SMRs. I think in the UK we are. In fact, the government announced the beginning of a competition yesterday for SMRs to fulfill about 16 gigawatts, which might be 30 or 40 SMRs in the UK by 2040, 2050. So this is a serious matter in the UK. This is the result of work that we've been discussing in Acumen 7, which is a group of people who've had a corporate background in construction and engineering. And I had 20 years in Rolls-Royce in the aerospace business and in the nuclear business. And so this is the other author is Simon Murray, who's bringing his experience of construction and civil engineering, and particularly his experience of lean methods for building the Terminal 5 at Heathrow Airport, which he was instrumental in, and in other parts now in the water industry and the rail industry in the UK, and contributing to a thing called Project 13, which is about alliancing modern methods and lean methods in construction from the Institute of Civil Engineers. So I've cracked through this, some nice pictures of nuclear at the beginning. But these are the big beasts, which are done in the traditional way. We have at the top EPR in France, which is a great reactor, but it's taken too long to build, as we'll see, and some AP1000 Westinghouse reactors in China, where they build a couple at Sanmen, and they're building some more. So I need to just put a bit of context about nuclear for this audience, I think. So the climate change, which is a serious matter in every country, has provided a new focus for all low carbon energy technologies, and specifically in the UK and in the EU, there's a commitment to get to net zero by 2050 for the whole economy, not just for power generation. This means effectively electricity generation has to be completely carbon free. The second point is the Ukraine war has focused minds of politicians in energy security, which wasn't really talked about. The market would deal with it. I talked about it as a serious matter in the UK. They published a British energy security strategy last year, which came up with this. We need more than 20 gigawatts of new nuclear by 2040. And the other thing is the old reactors, and we have some old gas reactors which go back to the 60s and the 70s, they're being decommissioned because of age. The earliest ones, the Magnox ones, have gone, and the AGRs are closing right now, and the last one will close by about 2032. The other issue is we've had an era of very cheap energy in the world, and that era of cheap energy is probably disappearing. It'll annoy a few people, but I think it's true. The end of the era of low-cost oil, and when you replace these with renewable systems, the cost of the renewable systems are somewhat higher than people think and perhaps recognize when you take into the costs of providing reliable energy from solar and wind. So it provides an opportunity for nuclear to compete. But there are some barriers to nuclear being successful. In many countries, the public attitudes are number one problem. In the UK, it's not. They measure this every 6 months. An independent university does this, and the approval rating's been over 50%, even during Fukushima more than 10 years ago, and it's regularly over 50%. And it's of course strengthened in most countries, the UK and the US, in terms of approvals in the last year or so. Disposal of waste is another issue. There is a technical solution to the problem, but it has political problems. Geological storage, it is being demonstrated now in Sweden and Finland. Other countries need to sort their politics out. It's a political issue as much as a technical one. The thing that really is stopping nuclear making a big contribution are its construction costs and the scale of these very large beasts that we make. These things are so large, gigawatts of power, and the costs are so huge that it makes them difficult to deal with. The projects are too uncertain for private investors. Ben Flyberg has just recently written a book on mega projects, including nuclear, and he shows that nuclear projects, on average, are about 120% over budget. They're too big to fund. That reactors cost 7 to 14 billion, depending on the variety you're having of these large reactors, and no private enterprise can raise that level of capital. It depends on government support. They're too slow to construct at the moment to meet market needs. Usually there's a lead time because they're all different and the planning is different, and then it takes about 8 to 10 years to build. And they're too expensive to be competitive. They produce electricity in dollars, 100 to 170 dollars per megawatt hour, which is way above what we're used to from gas-fired power, and it's way above what renewables are. These issues have to be addressed. And so that's really what it talks about. The first thing is I've got some data here, which is published about what's happened in the past. It's a slightly complicated chart, but I'll try and make it simple. So on the left, you have the US. On the right, you have the French experience. That US built about 100 power reactors. They built them into two groups. The group which was completed before about 1980, started in the 60s and 70s, and the ones done after that. The thing that divides these two offers is 3 Mile Island. 3 Mile Island accident changed the standards of design that are required, and also at the same time, there was a move away from the structure where the vendors were controlling the industry, GE and Westinghouse, and more open arrangements with each state picking its own vendors, picking its own architect engineers, doing own design mods, and bringing in huge variability. In the first group, the average cost was about the capital cost was about $800 to $2,200 per kilowatt electrical in 2010 dollars. And after this, with these two changes, the shock of 3 Mile Island and the change of policy to allow each state to do its own thing, meant that the costs, the mean cost more than doubled, but the variability went up hugely. And in this second phase, there were about 50 large PWRs and BWRs, which are still operating, providing power mostly in the US. They were very high cost. In France, a different thing occurred. They took a license from Westinghouse to build their reactors in the mid-1970s. And as a national effort, because they had no oil after the oil shocks of the 70s, they decided they were going to concentrate this thing with a single architect engineer, EDF, and with advice from Westinghouse and from Bechtel, and closely control these things and standardize them. So they built 30 900 megawatt reactors, slight changes between them, but very similar. And they built then 24 1200 megawatt reactors, again to the same license, but very similar. And they accommodated the design changes which were a result of 3 Mile Island in these 50 reactors. what you see is the spread is not large, and the mean value of the thing when translated into common dollars is less than $2,000 a kilowatt electrical. These are chalk and cheese and say something about programs, variability, and control. If you look at more recent reactors, the ones that are being built at the moment, EPRs in Finland and France, that they plan to cost about 3 billion, actually cost 11 to 12 for a single unit. They plan to take 4 to 5 years. It took 15 years. People can say this is the teething problems of new reactors, but it's something inherent in their very large scale and their one-off nature. French were not alone. AP1000s built in the States, the pair being built at Vogel. The plan was 14 billion. Price is going to be twice that. The plan was 7 years, it's going to be 14 years. People have analysed this and the reasons are quite well understood. There's little standardisation in the nuclear industry. Even when you got nominally the same reactor, the architect engineer, the local suppliers, the local customers wants lots of changes, and there are frequent design changes between versions. They're built mainly on site, what I call handcrafted on site, where there's very low site productivity because of the nature of these things. People haven't done them before, and they're crowded and complex places to work. And often the design's not complete before they start, and the frequent changes in the supply chain. Crucial to these figures at the top is that the US used to be very good at building nuclear reactors, and the French were, but actually there's 25 years since people have built them, and the lost experience, mainly craft experience, about how to do these things is key. And the second thing is because of the large scale of these projects, there might be 5,000 or 6,000 people on site. They run for 8 years, even on plan. They're very hard to control. Other research by the UK Energy Technology Institute looked at the 30 reactors, not the ones we're talking about, but ones that had been completed by the time they did this in 2015, in the years before this, and they identified some of the key elements which made a difference. First thing is, and probably the most important thing, is that know-how, that is things which are implicit in the craftsmen, the project managers, the team leaders, is much more important than people thought. People thought it might make a difference of 10% if you move people from one thing to another. Actually, it's worth 50% lower cost. That the strategies to improve the costs below the average, the baseline, standardization is a key thing, and this will come up again and again. Completing the design in detail before the start of construction. This is an anathema in the nuclear industry. They like to customize the design to the individual vendor or team. Construction by a consistent set of strategic contractors and suppliers. Stability in the supply chain, and multiple units built on each site. And we can see at the bottom the range, the very big range that it has caused. If you talk about the data collected in the US, the average specific capital cost in the 2015 dollars we have here is about $6,800 per kilowatt electrical. This is for single projects built by an experienced staff with all the traditional methods, basically handcrafted. That if you look at startups where people have not got the know-how and they are individual projects, the cost is 54% above that, $10,000 per kilowatt electrical. If you have experienced staff and use the best production technologies, you can get a third below the benchmark. And the best practices, which mainly have been forged in the East, in Japan and Korea, and to some extent in China, realized with the cost structures we have in the West are about a third below that. So the scope for improvement is huge. Next, I want to talk about what we did in SMRs to try and address this problem. The idea is these large projects mean you never get any repetition because they take 10 years and people either die or move off, and the cost is too large. So if you make smaller units, you can have more repetition, you can have people move from project to project, and you can get some sort of idea of efficiencies. So this is a typical cost breakdown of a unit, where the bought out nuclear island is about 12%, the turbo generator is about 12%. The biggest cost is project management and construction, all site-based activities. And for this project, we had to recognize that smaller units, there's this concept of scaling. You make large units because they're cheaper. So once you go to smaller units, you've got a headwind because scaling drives up the cost of plant equipment. So the ways of reducing this were 3: standardization, getting away from the variability, the design on every project, doing more upfront design. Production learning, so you use standardization and use factory-like processes to put better tools in place, and you have some repetition. And modular build, to take a lot of work from the very poor conditions on site into better conditions into factories, either on-site factories or mainly what we looked at off-site factories, and set up the right tools and equipment to do things properly. And we didn't just suck our thumb about this. This is some of the methods and the data we used. There's a reference light water reactor modularization scheme done by Stone and Webster on a Westinghouse design. So we had some detailed design information. We used some scaling of the modules, and we looked at road transport constraints to say what could be modularized. And this allowed us to look at the feasible modular shares for either large, medium-sized, or small reactors, and to allocate the degree of modularization you could achieve. We had a reference build schedule from the Westinghouse PWR that's built in the UK at Sizewell B, and from this we had all the schedule of construction and equipment and welding and a timescale for putting systems in place, and we used a time power scaling, and we calibrated that against the actual reactor build. And from this you can get build schedule model, and you can then flex the build time scales by size and modularity to see the benefit of that. And then we had a detailed reactor cost breakdown from the EDB, the engineering database from the States, where they collected data for 10 years and published it to a very detailed structure of plant equipment, cost codes and cost types. And we use cost power scaling to look at these across different sizes of reactor. And from this, we can get a cost model which looks at the variation of size, that's output of reactor, modularity, the amount of modulars you do, and standardization. And from this, you can get capital costs and energy costs. So I've got a couple of charts which are a little complicated, but I'll try and explain them simply. This is, it has the specific T-kick. This is a total cost including interest during construction. This is a much better indicator than the overnight capital cost for the energy cost of the reactor. And although most people look at the overnight capital cost, including interest is really a powerful way of looking at this thing. And the top line is saying if you use a conventional build and you just scale the cost of that in a dumb way, that you move up from the right-hand side where the typical large reactor is, you see that the cost is always going to be larger if you do nothing about it for SMRs. And some of the people say SMRs will never work because they looked at the scaling. Standardization takes design work out of the system and learning where you can to produce the same amount of power, you need to produce more units. And so for repetition, we said we have a 10 gigawatt program of reactors. If they're 1 gigawatts, that's 10 reactors. If they're 100 megawatt reactors, it's 100 reactors. And these two factors drive down the total cost. And then we look, that's the thick red line, still going up to the left. And then you bring in modularization, modularizing the main elements, the reinforced caging, the steel work, the systems, and even part of the concrete, and see how far you could go. And the different lines there are different degrees of modularization. And we find that if we get down to degrees of modularization, that's the cost share of modularization of about 60%, we actually have driven the costs down to a level where they are now competitive. It looks like it doesn't really matter what size of reactor you use at this stage, but the reality is a lot of these high degrees of modularization just not available for large reactors because the units are just so large. You can never get them down a road or on a rail. You've got to carry them in barges. It's just, the transport just stops this being possible. And so actually small reactors in the range 3 to 500 megawatts seem to be optimal, and you can access costs which are competitive. And I'll just show this on the next chart. Here is a 250 megawatt reactor example. And if we look on the left-hand side, we see what the large reactor cost is. It's costs about $6,000, an overnight capital cost, and something $8,500, including interest during construction. That's the first column. And if you just scale that to a 250 megawatt SMR, you see the cost goes up per kilowatt to about $14,000. The production engineering tools we've talked about are improve this. Standardization takes 16% out of this cost. Modularization at the 60% level, or 75% level, takes another 26%. And because the modularization allows you to build the thing more quickly, it takes another 16% to do with a schedule. And so you see a result, even without production learning, you've got a total cost, including interest, which is lower than a single large reactor. This is a really powerful effect. And then with learning for a 10 gigawatt program at a rate of 8 units a year, you can get the cost down by another 18%. And you're getting down to energy costs, which are interesting. So those are the technical ways we looked at it: standardization, modularization, and production learning. But these depend fundamentally on having a production system view. And this is the contribution Simon has really helped us very strongly with. And this is completely not the way the nuclear industry works the most. So what we're talking about is with SMRs, it's not just designing a new reactor. We're talking about designing a new industry, which works in a different way. So for product development, we have at the moment unique product designs, and the suppliers all do their own detailed engineering. We need to have standard designs instead of unique designs, and we need the engineering done by suppliers working together before construction begins. This is a non-trivial task and completely anathema in the industry. Process development, the way in which these things are going to be put together, people develop the processes along the way rather than beforehand. There needs to be much more development funding and involvement of suppliers way before this thing. For the main reactor and the fuel and all that, the people have done the process development, but this is only a small element of the cost of a reactor system. It's the less sexy items which take the time and take the cost. Supply and logistics, this is generally not centrally controlled. Each major supplier fixes its own logistics, and therefore you don't get the right flow of stuff onto these constrained sites, and you have a lot piling up. Really importantly, the organizational culture is key, and I think we're talking about lean systems in Toyota. This is quite clear in the Toyota production system. You've got to get people working together across many projects, and have incentives to cooperate to provide superior performance for which they'll get paid, rather than squabble over project by project, contract by contract, which is the norm. and the whole organization has to learn to remove the costs at the interface, remove the waste time at the interfaces, and work in a concerted way. This requires common systems. Those systems are quite complicated. They probably can't be set up and work efficiently on one project. They've got to be built over a number of projects. And then you need a structure of alliance boards to pull these people together. This is the sort of structure you see in the aerospace business. It's the sort of structure you see in the automotive business. The nuclear has to go the same way. And then for execution, rather than, it was very interesting, the 110% overachievement in huge backlogs, which is the focus is on scheduling and exceeding the schedule. And what we find is massive waste and massive slippage and a very poor, broken system. We need to map and model the production system and use the 5 levers of the production system to design the way through these things. With small reactors, building more of them, then the ability to do that is there. In summary, those people are very acute will see the backcloth at the top is 6 PWRs built by the French at Gravelines in northern France, where they, by more practical ways rather than scientific way, did a good job. But what the way forward for the nuclear is programs of standard reactors, and the reactor and the whole plant design of probably 10 gigawatts a program, which means 30 or 40 small reactors. Production systems with strong design control and integrated supply chains. This was put in place pragmatically in France and has been in China, in Korea, and they've got good results. More investment in design for modular construction, because they lead to cost reductions and shorter build schedules. You need a funding process which is really separate from what we're saying here. It makes that it's affordable and feasible, which doesn't really exist at the moment. And when people talk about competition, it should be competition between reactor vendors and their supply chains, rather than competition within projects and within programs. This competition can get a benchmark price, but it's very disruptive of the cooperation which is required to get an efficient enterprise.
Yeah, standard repeatable designs is pretty tough with that negative kind of competition. Very insightful, Tony. We got just a couple minutes for just a few questions for you. If you could stop sharing so we can see your face a little more clearly.
Yeah.
There we go. So first question, one reason integrated working is anathema to the industry is the hands-off way much government project management is carried out. An assumption of arm's length contracting. How will you address this obstacle?
Right. It is a big obstacle, and Simon's got much more experience than I have of it. But this Project 13 was something in the UK which was started by the industry and said, we need to hook onto this. That it has been adopted by an organization called the Infrastructure Project Authority in the UK, which looks after government projects and says, no, having a competition and free for all is not the most effective way for these complicated things. They both measure projects before they start and through the life to introduce these ideas, and they're very much emphasizing Project 13 ideas, collaborative workings and such like. We have got some good examples in the UK of them being effective. We need more examples to convince the doubters.
Good. That's encouraging. We need that. We need more of that in other places. Another question, has anyone reviewed lessons learned from how SMRs are built within the U.S. Navy nuclear fleet?
Yes, okay. So I said I was in Rolls-Royce for a while, and I was involved in designing nuclear submarine reactors. And so this is one of the reasons why I embarked on this thing. But the prime data about modularization efficiency, which was done in the UK as well. I mean, the UK was copying, I think America was leading. It comes from Electric Boat and Newport News, where they have been doing this for quite a long time. They did it on the Virginia class, which they built quite a lot of, and they're doing it on the latest reactor. So the same issues, it's mainly steel rather than concrete, but the same issues of congestion and access and inefficiencies because of that in a very enclosed environment mean that they get huge improvements in productivity from the trades by separating it out and then plugging it all together and welding the boat up. So yes, I think we have adopted those things, but again, perhaps because of the problems of secrecy of these things, it's very hard to transfer the knowledge into the civil space.
A good point. Well, thank you very much, Tony, for sharing your thoughts with us and your insightful research. And we look forward to PPI collaborating with you down the road and helping bring this to reality in the UK. So thank you very much.
Thank you. Thank you. Thank you for the opportunity.
You bet.